Hello everyone, my name is Humaira Banu. I'll be discussing now optimistic concurrency protocols and deadlocks. I'm currently in my second year of studying computer science and engineering at Srinivasa Ramanujan Institute of Technology. Let us see what is the outline of my topic. It is introduction, optimistic concurrency control and how it works, and deadlocks, comparison of optimistic concurrency control and deadlocks, some uses of this optimistic concurrency control, and finally conclusion. Let us start with the first slide, which is introduction. Concurrency control is essential in database systems and distributed systems to manage simultaneous access to resources. There are two key challenges which will be facing in concurrency control, like deadlocks and optimistic concurrency protocols. So what is a deadlocks? When processes are stuck in a waiting stage, then it is known as deadlocks. And optimistic concurrency protocols are nothing but a method to handle concurrent transactions with minimal locking technique. And concurrency control ensures that multiple database transactions can run simultaneously without any conflicts, maintaining its data consistency too. And the key goals are isolation, consistency, and atomicity. Here, transactions operate independently by avoiding any interferences, and the database remains in a valid state. And the transactions are either fully completed or not executed at all. And the types of concurrency controls are pessimistic and optimistic concurrency controls. Pessimistic involves locks resources to prevent the conflicts. Example here is a two-phase locking technique, and in optimistic concurrency control, it allows transactions to execute without locks, checking for any conflicts before committing. So let us see optimistic concurrency control in detail. The definition in here is a strategy where transactions are allowed to execute without locking, assuming the conflicts will be rare. So for this, we'll be using optimistic concurrency control, which in short called as OCC. The three different types of phases, the transactions in OCC or read phase, validation phase, and write phase. So we'll be seeing this in detail in our next slide. And till then, this benefits and challenges of this optimistic concurrency control is it reduces locking overhead by allowing transactions to execute without locks and works efficiently in environments with low contention. And it also consists of these challenges, like if conflicts occur frequently, as I have mentioned that the assuming conflict will be rare, will be using this strategy where transactions allowed to be executed with locking technique. And in challenges, let's suppose assume a case where the conflict occur frequently. It leads to high retry cost and more complex conflict detection, which makes the process to slow down. So this is the challenge we'll be facing in optimistic concurrency control. Now let us see how this optimistic concurrency control works. In three different phases, there are phases like read, validation, and write phase. In the first phase, which is in read, transaction just reads the data and stores in the values in private workspace. And then second phase, which is validation phase, before committing, the system checks if the data read by the transaction was modified or not by other transactions. And if there are no conflicts occurred, then the transaction is validated for commit. And in third phase, that is write phase, if validation is successful, then the transaction writes its changes to the database. These are the process how optimistic concurrency works. The simple three phases. So now let us move to deadlocks. What are deadlocks? The definition here is it occurs when two or more transactions are stuck, waiting indefinitely for resources locked by each other, making it impossible for any of them to proceed. Some of the conditions here are mutual exclusion, hold and wait, no preemption, and circular wait. A resource is assigned to only one transaction at a time, and a transaction that already holds resource is waiting for additional resource. And here resources cannot be forcibly taken from transaction, they must be released voluntarily. So this is the condition of no preemption. And in circular wait, a cycle of transactions exists where each one can hold a resource that the next transaction in the cycle is waiting for. So these are the conditions of deadlocks. and some of the causes, prevention, detentions, and recovery of deadlocks. Deadlocks happens due to circular wait, resource contention, and non-preemption. And the last one is hold and wait. Here, circular wait, which means the transactions waiting on each other, and the resource contention, which means competing for the same resource, and the resources cannot be forcefully taken from the transactions. And to prevent all these causes, we'll be using lock ordering, timeouts. Like, to avoid this hold and wait, we'll be using timeouts and lock ordering. And to limit resource requests, deadlocks can be detected by using a wait for graph to find cycles indicating a deadlock. If detected, the system can roll back transactions to resolve it. Recovery involves aborting a transaction to release resources, though it may cause some delays. This all covers the main causes, prevention, detection, and recovery of deadlocks. This some of the comparisons how this OCC, optimistic concurrency control, and deadlocks work. Mainly OCC, which means optimistic concurrency control, allows transaction to proceed without locking resources, checking for conflicts only at commit time. If conflict is detected, the transaction is rolled back and retried. And OCC is efficient in low contention environments but can struggle with high contention due to frequent rollbacks. Whereas, in contrast to that, in deadlocks, it occurs when transactions hold resources and wait indefinitely for each other, creating a cycle with no progress. So these are named, so that's why these are named as deadlocks. They are common in systems that use locking and require detention mechanisms or intervention to resolve. It can cause significant delays, especially in high contention environments, as they need continuous monitoring and handling to maintain system efficiency. So this is the key differences which we'll be seeing in optimistic concurrency control and deadlocks. The next one is uses of OCC, just like the applications of OCC. Nowadays, these are used in very huge systems like where the conflicts between concurrent operations are very rare. The first one is collaborative editing. Multiple people may edit the same document at a time. Like OCC checks for conflicts when saving the changes. The example I can mention here is Google Docs as well as Canva. E-commerce and inventory, like we'll be all using the online shopping, right? In this, the situation occurs when two or more users make to shop the same item at a time. So at the time the users try to buy the last item, OCC ensures no overselling when both try to check out. And in bank transactions, OCC checks if multiple users update the same account, for example, for transferring money to avoid any type of conflicts. And in social media, two or more people will be commenting or posting at the same time. This OCC resolves the conflicts. Mainly this OCC is used in a different type of industries or different types of sectors to mainly avoid the conflicts. The conclusion, the overall view of this is OCC offers a more efficient alternative to traditional locking mechanisms by allowing transactions to execute without locking resources, reducing the risk of deadlocks, and improving scalability in low conflict environments. Conflicts are only detected and resolved at commit time, making OCC ideal for systems with frequent reads and rare write conflicts. In contrast to this, deadlocks offer when transactions block each other while waiting for resources, requiring complex detection and resolution mechanisms. While OCC avoids the performance overhead of deadlocks, it may introduce conflict resolution overhead if right conflicts are more frequent, making it more suitable for systems with low contention and favor resource conflicts. So, thank you for your attention.